shut that door. Okay, perfect. Awesome. So why don't you start the presentation? Which group? Group one? Okay, go, present. So the way it's gonna be, we will have our presentation first half of the class, and then we'll take a break, and then we'll come back and we'll go over each of the presentation, and we'll discuss the problems, like the failures, and then we also have, let me share my screen. So what we wanna try to do, let me see. Hello. Yes, right. So then we'll go over the PowerPoint that we had in the lecture notes. Okay, and we'll try to match it up, like whatever the things we have here. You know, it'll be more like a discussion-based class. Omar, can you listen to that?
Yeah, I can hear everything.
Okay, good. So now I think we're trying to do it in a different way. I don't know if today is a trial class. You know, so sometimes if I cannot make it, then you guys still can come here. So still it can be the same, right? It's gonna be the same, right? So it can be done this way, maybe. Not sure. I'll try to give it a try. One class. How does it work? You know. Anyway, okay. So let me stop share, and then group one, you can go ahead and do the screen share.
Are we group one?
Yes.
I think so.
I think we had a good presentation.
Define a small control project, section 405.
Okay.
You gonna share your screen? Wait, let me do something. So I need to mute my screen and turn on. Okay, so later on we can do another thing is we can have a high sensitive microphone, and we can place the microphone here. So whoever talk, that microphone should supposed to catch everything. But if you talk something, can Omar listen that? Can I say something?
Omar, can you hear me?
I can hear, yeah, but I mean, it's not, I would say it's a little bit low, the voice, but yeah, I can understand what they're saying. If they get closer to the mic, I think it would be better.
Okay, so let's do one thing.
Yes. Okay.
Oh, can you hear?
Yeah, this is more clear. Yeah.
Go ahead.
Can you hear me?
Yeah, I can hear him. It's more clear. It's better than before.
So I think this is the best setup. We don't need to do anything. So this can catch up the speaker and the sound.
Yeah, exactly.
Okay, good.
So, good evening, everyone. We are Group 1. We are presenting today the effects of Hurricane Katrina on levee failure. We are presenting 3 people in our group. I'm Audrika Nahian, and I have Abdul Rahim with me.
And more.
Yes.
More. That's good.
So before going to the levee failure, let's first discuss what exactly levee is. Levee is usually a man-made or artificial structure built by people to protect areas that are near river, so that we can protect it from flooding and everything. So there are different types of levees that are used to help people protect their areas. Some can be material-based, like the earthen levee. Only earthen materials are used to build this kind of levees, and some are concrete levees. And the next we can see the rock levees. For purpose-based levees, we can see tributary levee. This is built just parallel to the main river. And then the setback levee, you can see the green vegetation there. It's built to protect the main levee from flooding. And then finally, you can see the ring levee. This kind of levees are built to protect a certain area in the river. Like the circled area inside is protected by this levee, and this is not only these are not only the kinds of levees, there are other kinds of levees also. So there are different types of levee failure. The most common levee failures are presented here, like overtopping, erosion of riverside, slope failure on both sides of the levee, and then piping and micro instability. And the main causes of these failures are severe weather conditions, and then river flooding, storm surges, and subsidence and erosion. So Hurricane Katrina was strong from 26th August to August 30. This was initially a Category 3 storm, which hit when it hit New Orleans, and it turned to Category 5 when it hit the northern Gulf of Mexico. The maximum wind speed of this hurricane was 139 knots. And here you can see the category division of which are the greater, how the hurricanes are categorized using Saffir-Simpson scale. And this is the path that Hurricane Katrina chose to travel while destroying areas. So at first in 26, it's after hitting Florida, it again gained strength and then traveled through the Gulf of Mexico. And then in 29th, this was calmed down. Here you can see the effect of Hurricane Katrina before and after situations. Like you can see all the neighborhoods inundated, and these all were because of levee failure. This shows us why levee is important for our day-to-day life. This is also another picture, and this is the catastrophic event that took place. And here I have added one flood hydrograph to show how much flood actually occurred. It's almost 12 times than the normal flood level that actually remains there. And this is also the water level and the predicted water levels that was supposed to be, but it became like this after the Hurricane Katrina. And this is the wave height, which was around 555 feet, the maximum wave height. And here I have added a video that you can see.
When Hurricane Katrina struck New Orleans, entire neighborhoods vanished under 20 feet of water. The devastation ranks as one of America's worst natural disasters, but also one of the worst man-made disasters. That's because since its early days, New Orleans has been sinking. The soil in and near New Orleans is a tenuous combination of silt, sand, and clay. Over time, the soil compacts and sinks. Before the Mississippi River Delta was developed, the river flooded regularly. Fresh silt from the floodwaters replaced the sinking ground and kept the land above sea level. But New Orleans is built to keep the river out. High walls called levees have been erected around the city to keep rising river levels at bay. They have also kept out the silt and sediments. Without the renewing sediments, New Orleans continues, ever so slightly, to sink. Its present rate is 3 feet every 100 years. Parts of New Orleans today are 8 feet below sea level. If another storm surge like Katrina reaches the levels, New Orleans will again be underwater. The odds of another flood are increasing because the ground under New Orleans is not all but shrinking. So are the surrounding wetlands. Every hour, another 2 acres of wetlands disappears under the sea. Like the sinking of New Orleans, the reasons are largely man-made. Canals dug through the wetlands increase erosion and destroy habitat, and levees help funnel the silt out into the Gulf before it can be absorbed by the coastal wetlands. Ironically, it is the wetlands, not the levees, that truly protect New Orleans from the sea. Every 3 miles of wetland absorbs a foot of a storm surge, acting as Mother Nature's insurance policy against hurricanes. Since 1930, Louisiana has lost over 1,900 square miles of wetlands. By 2050, many barrier islands will disappear altogether, not all of it shrinking. So,
What if making money was almost as easy as picking out hundreds of
Okay, so even though they claimed levy for this, I think building it and designing it properly also has an importance in the beginning. Now handing over to Abdul Rahim, the next part.
I know it all. I will talk about today about the hurricane protection system. The hurricane protection system consists either levee or like a levee combination with or a combination with of a levee and eye wall. Okay, and also it consists of a T-wall and bump stations. Okay, here's the New Orleans levee system. As we can see in the picture, the levees is along of the Lake Pontchartrain and also along of each the Mississippi River, and also each small creek in the in New Orleans city. And this is the combination between the levee and flood walls. As we can see right here, it's the T-wall. It's like a sheet pile installed in the ground, and also it's like right here combination between the levee and T-wall installed in the ground right here. And also the other picture, it shows like the eye wall and the sheet pipe right here installed in the ground with compound with a levee. Okay, the T-wall are in converted T-shaped concrete structures supported on precast or steel H-pipe. As we can see right here in the free body diagram, the T-wall, it's like kind of L shape. Okay, this is the side, the flood side, and this is the land side. And if we look like if we take a look beneath the T-wall, we can see the sheet pipe right here and the H pipe that supported the T-wall. And also this is the eye wall. The eye wall is type of flood walls, use cantilever steel sheathing driven through a levee. And as we can see in the picture, we have multiple types of the eye wall right here. As we can see in the free body diagram, we are seeing the sheet pipe installed in the soil, and also the concrete on the top of the eye wall. And right here, we got some like under seepage consideration. So for the first type, it's sheet pile cutoff. It is the common use in the levee. As we can see in the first picture right here, it is like a pile installed in the levee right here to cut off the seepage from the river or the water side. And the other one, it's often used. It is the land side to drain. It is in this picture, as we can see right here. It's going to be at the end of the levee from the land side. We got a filter right here, and the drain tube is going to be at the end of the levee from the land side, as we can see right here in this picture. And also we got the riverside impervious like a blanket. It is right here, a blanket in the side of the water, and a blanket on the land side to it's gonna be it's not gonna be allowed for the seepage beneath the levee. And the last one is gonna be the land side seepage berm. As we can see right here, it is on the land side. It's not gonna allow the water to get like on the land side. I think it's gonna be it's gonna keep the water like beneath the ground in the soil from this side. And also the pump stations, the pumping stations have not been considered to be a part of the hurricane protection system, except in a few instances, like where the buildings are a structural part of a levee or flood wall. And since much of the area is below the level of lake of Pontchartrain or sea level and the Mississippi River, the pumping stations are needed to prevent flooding caused by accumulated rainfall and seepage. And as in the case of Katrina, to evacuate flood waters after failure of the hurricane protection system.
So you have only 5 minutes to finish this presentation.
5
Oh.
minutes.
Yeah, just 5 minutes. It's
Okay,
supposed to be 20
this
minutes.
picture
So
also
First 20 minutes.
showed the whole the drain system. This is the drain system. Those the red points are the pumping station, and the others like the open and underground channels, pipelines, and natural channels, drains, and man-made waterways. And this is a video. I think we can.
Okay, so do you have the presentation is about how the legacy system will be implemented.
Mhm.
So do you have the case study here?
Yeah, Omar, he's gonna do the case
To
study.
hold the Gulf waters at bay.
Okay, I will do this video. You don't need that.
Here you go, Omar.
Thank you. So thank you, Udrik and Abdurrahim. So we had a report about Hurricane Katrina, which was a very big report, an extensive report with a lot of information. So what happened there, before I start talking about the performance of the levees, there is a recorded almost 50 or 55 cases of breaches from Hurricane Katrina. I just picked 2 of them to speak in general about them, what happened and all those stuff. So can you go to the next slide?
There you go.
So first, in general, this map shows the levee system or the hurricane protection system. The one was built before Hurricane Katrina, which consists of the eye walls, T-walls, and the levees. And you can see there is a large area of it, almost 70% of the levees were built below the authorized level, which caused that much problems to the levees. So before the Hurricane Katrina, the design was less efficient because they did not consider those hurricane events, and the maintenance was there was no developed programs for maintenance and inspections for the levees and all those stuff, which caused most of the problems from the hurricane. Can you go to the next slide?
There you go.
So this is one of the cases. I thought it's an interesting case study, which is 17th Street Canal Breach. So this breach, if you can see on the right side on the picture, the levee, this is a levee with an eye wall on it. The failure happened, pushed the levee 40 feet laterally. And when the flood dried out, they found that the levee is inclined 45 degrees. So when I was reading about the causes of this problem happened because of 3 major components. The first thing is the design, the soil, and the eye wall itself. Can you go to the next slide so I can explain? So here is the soil beneath the levee that failed. So the soil, as we listened in the video, it is consists of Holocene clays, which is oceanic sediments, and on top of that, the deltic sediments from the Mississippi River, and because Louisiana is down south at the end of the Mississippi River, which have very, very weak clay. It's the maximum is in this reach that failed, it's 900 PSF. Can you go to the next slide, which is so based on the analysis, the study, this failure happened because when we had the high level event water, it pushed the eye wall. The eye wall is the levee first is built on a marsh or swamp soil, and below that is a clay layer. So when the water started to push the eye wall, there is a gap developed in between the soil and the eye wall, which they did not consider in the design first. So this gap allowed the water to get between the eye wall and the soil. When the water gets in, that means that you have a full hydrostatic pressure over the length of the eye wall. So the eye wall started to tilt to the left and more water is getting inside. The water, when it's got inside, because the levee was built on a marshland, the clay below the main body of the levee was compacted and consolidated, but at the top was still not, it's normally consolidated. So what happens, the difference of the shear with the water pressure, with the high water pressure, started to push on the clay below the levee, which caused the shear failure and pushed the marsh. After the hurricane, they found the pieces of the marsh clay layer pushed away from the site. And then the whole failure segment failed. The next case study, can you go to the next slide?
Let me stop you here. It's a very good thing. Let's ask the question here, because I think later on it really doesn't make sense. Okay, so let's discuss it right now as you're presenting.
Okay.
So, you're talking about that there is a soft clay layer at the bottom, right? So
Yeah.
because of there is a soft clay layer, and there is another thing happening, which is the water table goes up, right?
Yeah.
So basically, it's not overtopping failure, right? It's just the push from the water.
Yeah, but they actually considered it as overtopping failure, but it did not seep over the eye wall. It caused on the flood side, the water happened. So the flood
Okay.
side.
So yeah, I get that. So my question is, what type of the failure is this? What is the basic failure happening?
Bearing capacity.
So this is shear failure,
What is shear failure?
which is basically the shear failure is the same as the bearing capacity failure.
Any idea from the audience? Piping? No. No way. Sliding.
No, it's not
It's not sliding. Technically, it's not sliding. Sliding means we have a slip surface. It's going up. Hydraulic uplifting. How you can have hydraulic uplifting?
Rotational.
What went wrong in this one? What went wrong? Also the question goes to more. It's not a shear failure. It's a different failure. It's a very interesting failure. That's why I stopped and started asking the question.
So as
What happened when the water went below the foundation? That wasn't supposed to happen.
Yes. So why it happened?
There was leakage in the
compaction underneath the foundation was not good,
Okay. So what happened?
so the water got seepage there.
No, water didn't get the seepage there. How the water can get the seepage? Seepage takes time. Seepage is not immediate failure. Seepage is a slow failure. It's a slow cook formula to have seepage. Seepage cannot take place overnight.
In fact, bearing capacity was impacted.
Okay, very good. Bearing capacity was impacted. It's a basically bearing capacity. What happens here, you have a soft foundation at the bottom, right? And what is pushing it? So the soil on the back side is basically working as a barn, right? So when the water comes in and pushed it, at the bottom you have a soft clay. So it's a sliding failure. So it just slide away. So when you slide away, it opens up. There is a gap. So if you look at the left one, you know, you have the original condition and the move condition, right? So it moved because you have a soft foundation side. So it pushed and it opens up. So when it opens up,
Now look at this. It's supposed to have a water on top, right? Water table is somewhere here, but it moved. So now the height goes down, right? So when the height goes down, now the water can overtop, right? So it moves. So the T wall, I think it's the T wall right here. So the T wall moved and water goes on top of it. Basically, it's a problem with your backfill on the backside. And the foundation failure. It's not a secret.
Yeah, so it was a composite failure between the foundation and the wall itself. It was an eye wall. There is no recorded T wall failures from Hurricane Katrina.
Okay, so it's an eye wall.
Yeah, it's eye wall. Yeah, so the second case study that I put, it was similar to this one, but the only difference is the foundation. This one was clay, the other one, the foundation. Can you go to the next slide? The other foundation, the next one was the foundation was sand. So when the gap happened and the water flowed in, it occurs like the normal piping and the uplifting, it pushed the marshland up and it caused the erosion on the toe of the levee, which caused the failure. So this has two different failures. The one on the south breach on London Avenue happens the same as the first case study, but the difference is the soil foundation. Instead of having the sliding and the shear failure, it was uplifting of the soil from the piping, because the foundation is sand and the water was flowing extremely or severely high. So it just washed away the soil from the protected side and it caused the failure. On the north breach, it is similar. The north breach actually is a sliding failure. What happens is just the water overtopped the wall. The wall was stable. They did analysis on it's called IPIT report. They did analysis after, they just simulated, and then the water has a factor of safety above 1. So it was stable, but what happened is the water overtopped it and caused the erosion and then pushed the whole eye wall and failed. Can you go next?
So basically, what type of failure was there? What is the key failure? The mechanism of the failure.
So the southern side is the same as what happened in the first case scenario. So the eye wall, it got pushed, the water flew.
Go back to the previous slide.
Yeah, so the one on the right, the south breach. So the water got in between the soil and the eye wall, and then it kept flowing to the sand, which caused the piping and the sand boils on the other side.
It's a sand ball, right? Almost?
Yeah, it's a sand boil. So it pushed.
So if it's a sand
clay
ball, then
cap-
what happened? What created the sand ball?
The hydrostatic pressure, the piping.
The piping. So it's a
Yeah.
piping first.
Yeah, this one is the only thing. The previous one, piping cannot happen because it's a clay. So piping can't happen. But this one, because it's sand, so it can happen, the piping. There is no shear failure. So it's going to be piping from the hydrostatic pressure. It's a high pressure of the water, which pushed the clay cap, which was like, I think, 2 feet of clay cap. It easily got pushed, and then the sand boils occurred, and then the whole section was washed away.
Okay, now the question is, what happens in a piping failure?
Soil gets washed away from underneath the foundation.
So it gets washed away underneath the foundation, right? How it gets washed away? What is the mechanism?
Seepage, water. Just uplift the soil.
Seepage water uplift the soil. So why only this location? Why not other location? Other location also has the seepage there and water. So why didn't create the uplift? Why this location?
Due to the geologic condition, soil condition in this particular place.
Has sand. Other location doesn't have sand.
No, some locations has sand.
There's an issue with the joint.
Well, it depends on the clay layer, like on the top of the sand. The clay blanket.
Hydraulic head related to hydraulic head.
Okay, first of all is the pressure, how much pressure is coming out. There are so many things connected with it, but the piping failure means, I just wanted to let you know for today's class, is like the piping failure means is going to have an internal erosion. You know, so it is like there will be like so much internal erosion when the water is coming out with high pressure. You know, that is going to create the piping failure. So if the soil is good enough or trying to cut down the amount of pressure, the pressure buildup due to the seepage, then it's okay, you know. But if the soil doesn't have the enough permeability, the hydraulic conductivity is a resistance. You know, always remember that. It's like it's resistance to how much water pressure is coming in, you know. So basically the question is, what is seepage? Any idea? What is seepage?
Water seeping through the pores of the soil due to capillary action.
Flow of water through a permeable medium
Okay,
due
but
to the difference of hydraulic heads.
okay.
Water
Tell it in a way so that my son, he's 9 years old or 8 years old, can understand.
water flows in a way that wherever he gets a
Minimum
Place to go.
resistance, water to is the path of minimum resistance.
Water goes through the soil because of the high pressure.
Then what happens? Okay, the water goes through the soil because of the high pressure. That's not the case. Everyone is saying that, but that's not the seepage.
wherever the water finds the void, he goes there.
Okay,
So-
let me ask you a question. I'm asking a very different question from a very different person. Do you know Ohm's law?
Yeah.
Ohm? Yes. Okay, what happens in Ohm's law? What is the formula?
If temperature is constant, the
Okay,
difference
the
between 2 point, the voltage difference between 2 point is proportional to the current flow between these 2 points.
Okay, just tell me the formula.
V equal to IR,
V equal to IR. Okay, so what is V?
voltage difference,
Our potential difference?
Yeah.
Okay, what is I?
current
Our flow,
flow of electron.
and what is R?
Resistance. But V equals to Ki. K means hydraulic conductivity, I means hydraulic head.
Okay, so what is seepage?
Seepage is I. Seepage is K,
What is K?
hydraulic conductivity.
K is resistance. So how current pass through the wire? From higher potential to lower potential, like when you have a voltage difference, right? What happens there?
Travels from high to low.
Okay, but there is something there. What is something? You guys are working with it every single day with it. What is that? The resistance, right? Or the resistivity, right? So what is resistivity? Apparent resistivity or the relative resistivity? What is that? Every material has a resistance against the flow, right? So when the current is flowing from one point to another point, it has to do some work, right? Isn't it? It needs some energy. So every time the current is flowing from high voltage to low voltage, it loses some energy, right? Okay. So along the process, what it does, it goes through it and it loses some energy, right? It goes down. So from the high power point to the low point, it has some loss. What is seepage? Exactly same thing. It goes from high point to low point, and soil is going to give you the resistance through the hydraulic conductivity. So it has some loss. Every unit length it travels, it has some loss of the pressure, right? So it goes from high pressure to low pressure, right? Now let's say why we have internal erosion. It goes through from the high pressure to low pressure, but soil doesn't have much resistance. So your pressure is high enough, it can break the soil particle.
Yeah, because it's sand.
Because it's that.
Yeah.
then you have, that's how you have the pipe. Can you feel it? Participate?
The loss of water energy that's.
So,
happening, the-
seepage is water is flowing through the soil under pressure, right? And having the law. Having
Current. This is current.
Seepage is not kind, the whole thing is exactly the same thing, works the same way. You know,
Equivalent to current.
yeah, very similar to that. Exactly same way, no difference. Got it? Continue.
Yeah, so this is what we were talking about. The foundation was sand, which caused that piping of the eye wall of London Canal. Can you go to the next slide? So this is the last slide, which, as mentioned, the majority of the failures was because the overtopping failures and the erosion, internal or external erosions. There was like a recorded 50 levee failures from the hurricane. So this here, there is the first point talks about the levees with a clay foundation. Let me take this away. Yeah, so because of the levee opening between the flood wall and the soil, the water rose and caused the high hydrostatic pressure, which caused the shear or the sliding failure. And then the foundation with the soil with permeable, which is sandy soils, it has the high hydrostatic pressure caused the piping and pushed the clay cap and then washed away the whole failure. And yeah, as I mentioned, there's no breaches occurred from other reasons other than overtapping from Hurricane Katrina, and there is no T-walls failures, and that's why they are now shifting to design more T-walls for hurricane protections. And they are like in New Orleans, they are going over the levees every 3 or 4 years and increase the crown of the levee with some 1 or 2 feet of soil. And then now the new design after Hurricane Katrina, they designed the levees to be overtopped. So they design, either they put a seepage berm on the protected side, or they just add the T-walls, which with the battered piles going up to 100 or 120 feet down, so it can overtop and stay stable. Even the erosion will not flip the T-wall. Any questions?
I have many questions.
Yes, Dr. Khan.
Okay, the first thing is what went wrong?
What's that?
What went wrong?
What
Went wrong?
What went wrong? First, as I said, the inspection programs, the design of the levees was not up to the flood. The foundation of the soil also was not designed properly. So I don't think it's somebody, I think it's just, it was not expected to have this strong hurricane. So the design was not sufficient to withstand that.
In that YouTube video, I saw that the levees were actually building the funneling effect, which elevated the flooding conditions there. Instead of that, the swamps would have been a better solution for this New Orleans levee problem.
The swamps could be better option. So
Yeah.
it means the swamps means like you are allowing them the free flow of water. So it's like as a reservoir, it will behave like a reservoir, right? Whenever the water comes in, then it has like more area to flood. The natural system. Wow. Okay, so then what else? What is the major lesson learned from this failure?
We need to check the geologic condition much carefully.
Okay, so it's basic for anything, not from only this.
I think instead of being responsive to the results, trying to be proactive to try to mitigate the whatever causes the problem, instead of, because what we are doing now is just we respond to the issues after the problem. We wait for the hurricane to end, and then we go back and fix this and do this and do this, and we react after that. So probably being more proactive is good.
Let me ask you the question. This question I'm asking to the Army Corps engineer Omar, not to the student Omar. Do you think it's possible to be proactive in terms of the funding? And in terms
Funding?
of zone?
I mean, no.
Okay, end of the story.
They're
So-
actually paying billions every year, and it's not enough.
Well, the way it works is designed to fail. You know?
Yeah, it's not designed to overtop and fail and whatever.
No, it is not on the lab. I'm not talking about the levy. I'm talking about the system. The way the system works. The system is not. But I know that people are working really hard to change it, but it's not easy. But yeah, it's really great to be proactive. No doubt. But it also, I think we are like 10 years away from there in terms of the technological development and the policy-based change that is needed to move from the proactive system to the reactive, from the reactive to the proactive system, you know, because the first thing I pitched this idea to a Geo-DART engineer, and he freaked out to me. So, but anyway, it's a very good presentation, excellent presentation.
Thank you. And the report it's like 11 volumes. It's almost 1,000 pages. So we just discussed 3 chapters, but it has a lot. So I can share it with everybody. I mean, it's on the internet. It's available.
Okay, so
Public
I
information.
can send the report to everyone so that everyone has it. Do you know? This is my last question. Wait, no, it's not my last question. I have 2 questions, but let me ask you why the T wall are not failing, but the I wall are failing.
Well, the T-wall is because it has the when they build the T-wall,
Go back to the drawing of the T wall. You have the drawing of the T wall.
yeah. So the T-wall got 3 components: the wall itself, eye wall for seepage to cut off the seepage, and the piles going like up to 100 or more than 100 feet to
Okay, look at these parts. Which one is T wall? And
it's on the right, the T-wall on the right.
Okay.
Can you go? Yeah.
Yes, is there. Now, why the T wall is not failing, but I wall has failed. Look at this diagram and then.
Because of the sheet pile and also the H pile inside
The T-wall got also more passive resistance on the protected side. You see
Very
that?
good. Yes, T wall has more passive resistance on the protected side.
Yeah.
It's by default it's built in. It's like, you know.
Yeah, the eye wall is the same level.
I wall, okay. I wall behave like a laterally loaded pipe, you know. So it allows the lateral displacement because the lateral displacement comes from the point of fixity. So if your point of fixity is not being developed, then you'll have more movement, right? That's how it's being. That's the basic, you know. But if you look at the T-wall is like a retaining system. So and that retaining system is supported with the pile, or maybe not supported with the pile, but you always have a more passive resistance because of the foundation of it. You know, that's why the T-wall is performing better. It's just a mechanistic problem. There is no slippage, nothing else connected with it.
But
Just
it's more
because of the
expensive.
geometry.
More expensive.
Okay. Yes. Now, do you know what is in the recent flood, recent hurricane Ida? During the Ida, there was no flooding, right? Or there was no breach,
No breaches. Yeah.
no breaches. So it was the litmus test for for the design, new design, and it was really well. So, do you know the cost of that project?
It's got to be high because it's just like regular projects now developing, increasing levies and all those is costing like 900. And I mean, the budget for New Orleans hurricane protection from Congress every year, it's $950 billion.
$950 billion.
Uh-huh.
Okay. Look at the number. Is it billion or million?
Billion.
Billion. Good. Thank you. Okay.
Just for New Orleans.
Wait, there is one more question. Sorry. The last question is, the Hurricane Katrina changed something in our civil engineering design because of all the breaches caused by Hurricane Katrina. There is a major change in the civil engineering design. What is that?
Safety. Well, they changed a lot of policies, a lot of design methods, design
Yeah,
guidelines.
but it changes. It made a major change in the design standard. What is that?
It changed the way we consider the return period.
Very good. What is the return period?
Usually we used to consider 100 years. Now I think we use like 500 years.
Yes, excellent. That's the major implication of it. Very good. I don't expect anyone can answer that. Very good. Excellent. Yeah. So that's the major contribution of the Hurricane Katrina. After Hurricane Katrina, AST recommended that the return period for this design should be shifted toward 500 years. And this is how they are trying to fight the climate change. Okay. Now I have another question with you. Do you think considering 500 years return period is working for climate change?
No.
Why?
Changing in a.
Because it is not economically feasible.
It's not changing in a
The
certain
change is
way.
not constant.
It's not linear.
The change is not linear, as he said. It's not constant. We need to have some very good models to predict up to 500 years.
And it's abruptly changing. It's like it's not following a single path.
Okay, it's not following single path. This is the system dynamics has changed. So all your model parameters that is being used for the 500 years return period
Are changing.
and your initial condition are different, right? Your boundary conditions are different, but you're trying to fit in the same number. You know, it doesn't work. So it's not working. That's why. So all the weather model doesn't work. Most of the weather model predicts really bad. You know, you'll see that there is no forecast of rain and it's raining, or there is a forecast of rain and it didn't rain at all.
Well, I think we can predict rainfall in short duration very
Accurately.
In
No,
short duration up to 7 days.
no, it's not working. It's not working.
Back in Bangladesh, we have a flood forecasting system in our organization that gives somewhat 60 to 80% accuracy, where predicting the discharge rate in the rivers.
60 to 80% accurate.
I think.
Yeah, the 60 to 80% accuracy is not accurate. Okay, because we are trying to pinpoint the rainfall, let's say. The reason we are gonna do that, I'm discussing that because let's say we wanted to be proactive. Proactive is all about optimization, you know. So we need to bring the system engineering. Do you know what is the system engineering? Any idea what is system engineering?
System.
Procedure to do something.
One more?
System engineering,
Yes,
knowing the process and control it.
knowing the process and control it. Give me an example.
I mean, understanding the whole parameters around you, the whole system, and then knowing how to react to it.
Okay, give me an example. A simple example.
I would say a school class. The professor knows all the components, the students, and everything, and then he arranges and manages the class in the way it depends on the study.
Okay, it might be possible, but you're you're giving example in the hypothetical way.
Yeah,
Okay, specific.
The comprehensive engineering management.
Okay, but in the UK, I guess can go and say. What is that?
Like from initiation design and the management of the project
Of the whole system.
of the whole system.
Give me an example, very simple example. Give me one simple example.
Of the time, like we start from watching the location, then we design, then we construct.
No, it's still not a system engineering. It's still not a system engineering. The system engineering, the best example for system engineering is building a car. Okay, building a car. So let's say you have a car. In the car you have the motor or the engine, right? It works a completely different way. Then you have a AC unit, which is HVAC, works in a different way, right? You have all the sensors and all those things for the safety, works different way, right? Then you have all the entertainment system, works different way. Those are all different systems, right? But
Combined together.
you combine it together to make one system, right? So now when you combine it together to make one system, you need to make a optimization of all the systems, right? Tell me another product who did the master of the system engineer.
river, Mississippi River.
No, not you.
Apple devices.
Apple devices, very good. The iPhones. The iPhones are the great example of the system engineering because they are perfectly optimized. You know, they're perfectly optimized. Their camera, their RAM,
Thinking
their
of selling your house? Want to know how much more you could be getting by using this brand new way to sell? The real estate market is rapidly shifting. So if you're thinking of selling anywhere in the Jackson metro area, including the
Hey, Amber.
It's okay. Stop here. Stop here. No, that's fine. So, okay, so the system engineering is okay. Okay, so in terms of that, if you want to be proactive, you know, then you have to have the models for the system engineering to know like when to do something. Anyway, okay, the next group. It took one hour, the first presentation.
He's online.
Okay, if we can wait. So the third group, you can go.
Is in Dr. Ven's class.
Yeah, I know. So I think it's get done by 7:30 or so.
How is our class gonna stay? Tuesday or Wednesday every week?
It's gonna be Tuesday.
Okay.
It's gonna be Tuesday because Tuesday I can make it in person. If it is Wednesday, then I have to do it at home. But you know, there is a fire watch in this area. There might be a wildfire.
Rain release will do it.
Okay, so that's another one. Okay, great.
Good evening, everyone. Our presentation is on actually Teton dam failure. This is our group member. I am Sam Hussain. The presentation is actually consisting of three parts. The initial part is the introduction to the Teton dam. Then comes the
Why is
structural elements of the dam.
the camera is not working?
Okay. Yes, it's on. It should work now.
Okay.
And finally, we'll discuss on the investigation or the probable cause of the failure. So, Teton Dam is actually located in Idaho, USA, which is actually on the valley of the Teton River. It was constructed in 1975. It was basically constructed for the purpose of irrigation and generating hydropower and flood control. And the drainage area of the dam was around 853 square mile. And the type of the dam was basically earth-fill dam. And the elevation, total height of the dam was 350 feet. And the total length of the crest was around 3,000 feet. So the total embankment actually consisted of 5 zones. In zone 1, there was impervious center core. Actually, there is a picture of it like here. This is the zone 1. Then there comes the zone 2. It's actually overlay of zone 1 and extended downstream. So to provide a layer to control seepage through the foundation. Then that's basically zone 2. And then comes the zone 3 here. It is actually mainly it's on the downstream, and the function of the zone 3 is to provide the structural stability. Here we can see this. And in zone 4, it's actually consisted of the storage areas downstream from the control structure and the temporary enclosure here to permit the work to be done. And finally, there comes the zone 5, which is the actually rock fill of the embankment. And that's the foundation details of the Teton Dam. In the Teton Dam, the foundation was around 21 meters deep. And the key trenches on the abutments above the elevation was 1,550 meters. Besides, there was a cut-off trench of rock below the elevation of 1,550 meters, and below the foundation there was a continuous grout curtain to block the seepage of water below the foundation. The next part will be presented by Fahim.
Hello everyone, good evening. So now I will be discussing about how the failure was, how the failure placed. first of all, let us see the picture here. So this picture is from the failure was occurred in June 5, 1976. The failure started from here to there. So what happened actually in June 3 in 1976, they observed two small seepage. And after that, usually what happened is like every week there is an inspection of the dam. So after getting this, knowing the seepage of the two seepage on June 3, they decided that they will do the further investigation twice a week, like that. At that day, the seepage rate was like 500 liter per second, and no overall evidence was there. But in June 4, as of 9 p.m., there was no further occurrence or evidence. On June 5th morning, they started observing big seepage. If you see this is a picture for the June 5th. So it started here, from that small seepage, it went through the big sinkhole, and suddenly it got collapsed. So what was happening is when the dam was constructed in 1975, from October to April 1976, they started the filling water very slowly. So the initial elevation was like 5060 feet, and in April to 1976, the elevation was 5160 feet. But suddenly, from April to June, the filling of water got increased a lot, and within from April 10th to June 3rd, June 1st, they fill up the whole dam, or around 160 feet, and the final elevation was 5320 feet. So these reasons, so when June 3rd came, they started watching that small seepage, and June 5th morning around 7:30 a.m. they saw that muddy water was coming out from that seepage, and the elevation was like 5200 feet, and from the right part of the embankment. So they started observing how to fix those things, and within from 7:30 a.m. to 10 a.m. they saw that a big whirlpool was getting shown in the dam, and they started bringing 4 bulldozers to place some ripraps and hold the failure, as it was getting bigger and bigger in a very short time. So when they took 4 bulldozers, 2 bulldozers went into the failure area, and the other 2 were there. So, and suddenly in 11:55, the whole system was collapsed, and then in the evening they changed the whole they emptied the whole dam, and because of that, the 5 counties was flooded, around 3000 square mile area was inundated, and the distance travel 155 mile. And overall, when the dam was constructed, the budget was like $250 million, but when and within 6 months, what happened, 40% of the budget went out within first within 6 months after this failure. And there were claims of around $400 million was claimed, and they provided around $140. The government repay them. So after this failure, there was an investigation team came, and they investigated the whole scenario, and the investigation, the failure procedure will be carried out by my fellow classmate Said. Thank you.
Thank you, Fahim. Everyone, I will discuss the investigation. From this investigation, it was found that volcanic rocks of the site were highly permeable. So far, I have read from the report, 2 kinds of volcanic rocks are available in the foundation sites. That was basalt, and another one was rhyolite. The soil classification was found to be ML, silty sand, which is mostly. Another investigation covered that the grout cap was not adequately sealed, and hydraulic fracturing was very much possible in that setting, existing setting, in that time of that moment. I'm talking about the scenario before June 3, 1976. And initially, there is no evidence of differential settlement was found. And seismicity was not a factor for that zone because Idaho is not in a seismically active zone. So, probable causes of the dam failure. There are many causes that are discovered in an independent study done by University of North Carolina, Charlotte. I just pointed out few of those. There are the series of design and construction deficiencies was involved there in that time. Foundation treatment was not enough. Permeable foundation material was a key responsible factor. The geologic investigation found that. And there was a rapid filling of water just before the June 3, 1976, which deteriorates the stability of the whole dam. And another significant factor was bypass of the ground cartilage. So what lessons can be learned from this failure? It was a very catastrophic failure. I found a news report of that time. A man was just sitting on that levee just before the failure. So it was really a sad story. So what lesson? Downstream defense we should really focus on in case of safety. Ground cutting construction, there should be careful considerations should be made. Warning systems should be developed based on the technology available right now. And that's all I can say about this. Thank you.
Good. I have many questions. First of all, what is the damage caused by this failure?
Five counties were inundated, and
11 people died.
11 people died. Around $200 million got wasted within for the dam, and that the flooding and the flood control thing and the hydropower system that got collapsed of that area, and like there were like 20,000 people were homeless at that time. After that,
How it becomes homeless?
because that area got inundated like 300 square miles.
Is it inundated or is it smashed down?
The dam got smashed down, then it got inundated.
How many city it just smashed down completely? Have you seen the video?
Very old video.
Like the report was published in 1977.
Okay.
Now the thing got the occurred in 1976, but the report got published in 1977.
There are many reports and many papers published.
The basic one, the first one.
Okay, so
1977.
1977. Okay, so how many cities or how many counties?
5 counties.
5 counties. So how many? So it's like 20 homes are destroyed, or it just they are displaced. Displaced is one thing; they can come back. It's like there's flood. So the flood water was there for maybe 3 days. They can come back and they can repair it. But have you seen a tsunami? So how much water was being released when it failed? Do you have an idea?
Initially, it was for the first day. It was like 500 to 800 liter per second.
What is the total volume
Total
of water?
volume. The elevation was 5320, 5060. The length was
How many gallons of water has been released in an area? Can you start? What is the volume of the water released from the Teton Dam?
80 billion gallons.
80 billion gallon, right? So if 80 billion gallon of water is just being released
Within like
With-
1 hour.
within 1 hour, with what is the height?
It was 300 feet.
300 feet. So how much potential energy is sitting there with that water?
Tremendous.
Tremendous, right? So it's like a nuclear bomb blast. You know, the amount of energy is being released. The same as like an atomic
Explosion.
explosion, right?
It was a design issue, right? It was the design of the dam.
Okay, now, what is the talking about? Basically, what went wrong?
Yeah, because from what I see from the picture, it was high, the hole. It was not under this, like at the base of the dam. It was almost above the middle of the dam.
Few things take place. The first of all was they didn't study the whole geology.
Okay, that investigation was poor. Okay,
Secondly, they started filling the water. For the first 6 months, it was good. They put like for first 6 months they put like 160 feet water, and then within 1 month they put like more 150 feet, 140 feet water. After that, like within 2 or 3 days, this incident happened.
And filling material was really low quality.
how do you define low quality filling material?
It was permeable actually.
It is permeable, okay, very good. So, what went wrong?
Piping happened.
Internal erosion.
Okay, so this is the major failure because of the piping, right?
Here it is one of the major failure according to the report.
Which one? This is a piping failure. Basically, it's a piping failure.
And there was a flow and another detailed study said that flow beneath the foundation. There was a thing called ground cutting.
Well, okay, go back to the section and show the ground cutting. Which one is the ground cutting?
The ground curtain is probably this one,
This one. Which one?
beneath the foundation.
In the foundation. Okay.
That is ground curtain and water flow beneath that ground
So
curtain.
what is the ground cutting? Basically, what is the use of the ground cutting?
Ground curtain is basically we'll dig a long hole.
Okay.
And we place grout in that hole.
It's
like a
basically
foundation,
to compact the soil through concreting, through using the use of micro concrete to the soil, so that water can't pass through the.
So is it creating like a cutoff system?
Yeah, like to stop the seepage from the body.
Okay, stop the seepage. Okay, very good. So it's a grout.
Bentonite.
Okay, it's a grout curtain, right? It's also known as the slurry wall,
Yes, yes.
right? Okay. So basically, the quality control was bad, right?
Yeah.
Is it a design problem or is it a construction problem?
Construction problem.
It was primarily construction problem.
But design because
There are some issues with
bypass the
design.
ground curtain too. Bypass the ground curtain too. The water.
Okay, and then in these things, there is another factor which really contributed the whole thing.
Hydraulic uplifting.
Sudden pressure, like sudden water pressure.
Floating formation type problem.
Can I check the construction time?
Construction delay.
Construction time.
Consolidation.
Construction time.
It is in 71 to
How
75.
many years?
Saturated.
3 years.
They use saturated soil.
How many years?
3 years.
3 years.
3 years, right?
Yeah.
And what is the size of the earthwork?
Huge, it's huge.
Huge,
Give
right?
enough time to
Consolidate.
consolidate the soil.
Okay, it's not a construction problem. It's a management problem. Why there is a poor construction?
They made it hurriedly.
They're rushing,
Yeah.
right? They are rushing, so they didn't do all the quality control things they're supposed to do. All they wanted to do is like get it done, get the credit, and move forward, right? So who built it?
Who build it?
Yes, which organization built it?
Bureau of Reclamation.
Okay, very good. Bureau of Reclamation. What is the abbreviation of that?
Politics.
Okay, what is the abbreviation of that? USBR.
USBS, yes.
Okay. The USBR built many dams. All the large dams are basically built by the Bureau of Reclamation, right? But after this, there is a significant change in some policies, and there are some significant changes in some regulations, in the federal regulations. You know, so one of the most important learning from this campaign
The construction management.
is very important.
Investigating the site first.
Okay.
Time is a key factor here. So we need to give time to the proper timing to the certain things that should not be ignored.
What is the most important learning?
Proper selection of materials.
You cannot do that always. Honestly speaking, this is one of the major engineering problems now. We always try to select the proper engineering material. The better idea is to engineer it properly, not selecting the proper engineer. So whatever the material you have, if you can do the engineering, the right engineering, you still can build it. It's not a problem. You know. So, but there is one thing that is really important. All the construction projects, everyone has the experience working with the contractors, right?
Yeah.
So every contractual work, there is one thing.
Quality control.
Okay, but before
Cost, low cost.
Okay, low cost, there is another thing. Okay,
Waste
so the way the tendering and bidding thing works is a different thing. But there is always some demurrage. The contractor needs to pay a certain demurrage if there is a delay in construction, right?
Yes. Yes.
That demurrage doesn't count the quality control, right? Even if the quality is being sacrificed, you have to achieve the time, right? This is the perfect example of that. What goes wrong? Because the contractors are extreme pressure to get it done
By time.
by time. So they sacrifice the cost.
That's why
They build the whole system in a like one.
there was a huge problem with
They
the
sacrifice the quality. And when they fill it up, they are supposed to fill it up and monitor it, right?
Exactly.
They didn't do that too.
So when like in April it was good,
Yes.
but from April to June the scenario got changed.
Because let's say you build something, then you have to commission it, right? So how do you do the commissioning? You fill it up, you monitor it. Then you fill it up, you monitor it, right? Then you fill it up, you monitor it. You just build it. You don't know how it's performing, right?
LiDAR from clouds and turn them into raster surface models using ArcGIS.
Everything you wish for. Your site traffic is
That allow you to work directly with point clouds in our native.
Amber, can you?
Okay, so
And it started from the elevation 5200. So till April the elevation was 5160 and the final elevation was 5320. So the problem was in that middle.
Okay, so basically they don't have enough time to do it right.
There is a triangle called cost, quality, and time.
Cost, quality, and time.
So whenever you focus only on one thing, then the other two has to be compromised.
Compromise, okay. Yeah.
So it says that you have to comprehensively focus on all three.
All three.
Otherwise, one of them will be compromised.
Okay, very good. There is another thing is coming. It's gonna change it. There's gonna be carbon.
Climate change.
Yeah, it says like there should be another, like, for example, if you look at the Google map and the way they give you the recommendation. Right now the way of recommendation has changed. Previously it used to be the lowest time. Now it becomes lowest emission.
Yeah, when you try to select flight from Google Flights, they suggest low emission.
This is true. Which one is the low emission flight, right? Not the cost. So whenever we are looking at the cost is always the short term thing. You know, we don't assess the life cycle cost. So that's how all the damage we made the climate, you know. But if we change our paradigm and we look at the broader perspective, then it comes with all the other things too, you know. Okay. Anyway, very good. Thank you. Okay, I have sorry, I have one last question. This question belongs to everyone. Look at the design. That design has so many zones in it, right?
Yes.
Why they have so many zones?
Different layers.
Yes, why?
Availability of the material. Availability of material.
Construction stages.
For global stability,
What global stability?
sliding, overturning, and bearing failures.
Okay, then how it is this different zone? How this different zone is giving you the stability?
So some of the zones are meant just to like stabilize the toe, and some of them is just to prevent seepage. Apparently, seepage happened.
Yeah, but yeah, you're right. So basically, each of the zone has its own purpose. It's not based on the ability of the material. You know, it's not. It's because of you have different zones, and through each of the zone has a different purpose. You know, so basically there are like different type of the failure for the dam. So you can do the design in a way so you can basically control each of the failure, you know, in a cost effective.
It's like a modular design.
Kind of. And this is the best design, you know. And the worst possible design is like a one size single field, like the same type of material and it just bringing all together and just build it.
So the design was good.
The design was good. The design was good. The only challenge they faced is the extreme time pressure. And who creates the time pressure?
Government.
What?
Politicians.
People who
What?
give money. People who give money.
They have some
Why?
political commitment.
Maybe they're
Basically, yeah, this is the right thing. They are the political.
maybe there was election. Maybe there was election.
Maybe there was the election. They want to win the vote. You know. So there is always a pressure, tremendous pressure. You know. There is a tremendous pressure of getting things done by this time, so that you can have you can is like the commitment is being achieved. right?
True for everyone.
For all regions of the world.
All regions of the world. And then what is the challenge in this system?
Quality is compromised.
Quality is compromised. You know? That's the basic. So what is needed?
To coordination of quality and cost and time.
Politicians should be educated.
We should not talk about that. This is not a part of that. How we can solve it technically and such. This is the reality, right? You cannot change it. So how about like you can make it a technical solution?
Basic approach should be increasing the factor of safety.
Have some cushion. Always having a cushion in the design, right? Don't do excessive design. Always, if you say it's a government project, always try to have like more cushion in it. So if something goes wrong, you still have something, right? But it's not necessarily only government project, for any project. It's better to have a cushion, right? But also, there is one key thing that can be replaced very quickly.
When we are doing the aggressive design, the cost is going up.
No,
Down.
down,
So yeah, sorry.
down. When you do it,
So we can't do aggressive design.
you can, if you have the control. And you know, in this case, what happens? This is a very interesting concept. But in this case, what happens is, right now, in many government contracts, there is a design is like the like different teams to different work, and there is no coordination between those. Instead, now the big projects they try to do the turnkey basis, which is the design, build, and operate. This design. So if you do it design, build, operate basis, then the team
One person will be liable.
will be liable, right? So when the team is liable, they always try to do a good job because they are managing everything, you know. So it cannot be done every time, but this system really works, especially for big projects.
And build system.
Design build system, a single party is going to do everything. So let's say you give it to the contractor is going there, and then they will hire the designer, and they will work collaboratively with the designer, because when you build a system, there are many changes will come built in. And now if there is no coordination between the design and the construction, there is a big point, you know, because the contractors, they'll just build it because they have a time pressure.
They just want the money.
Yeah, there is a time pressure, and it's an open secret for everybody, you know. So no matter what you do, it will be there, right?
But in the turnkey system, there is also a problem. It is actually applicable when the client doesn't know what actually he wants. Like in the normal system, we actually dictate everything that you have to do specifically this, and this.
Yes.
But in the turnkey system, we just call them build a dam here. Now it's your duty. So it has the pros and cons. Like you don't have the control over the money or the costing. And the other, but whatever you said that the design and construction team, the contractor, is solely responsible for this. This is a good thing because the coordination, the total system, the total management is very good. They really do it within a time frame, maintaining the all aspects. But in Bangladesh, I'm actually referring some of the projects from Bangladesh. They are like in some cases the client don't know actually what he's going to receive.
Okay, so what is the problem there? Okay.
The problem is that actually the contractor. And the contractor is getting actually gaining more profit, but actually he deserves.
Okay, but I have a question.
Actually, I think the main problem, if we summarize this, is that there is a breach of trust, I guess. The procuring entity or the procuring entity is hiring a contractor, and he has some kind of expectation, but he doesn't know what he wants. But when the contractor gives
Something.
his best effort with the money he's offering,
Like for the bridge.
that
We
was
wanted for the
we-
bridge, but the drawing design and everything was done by this.
Okay, so in this case, basically for the design build type of system, the first thing needed is a preliminary design. So the client is supposed to have a consultant who should listen to the client and do the preliminary design of it. And the preliminary design are the recommended method given by the agency and given to the contractor. And then the contractor is supposed to come up with a design build team who will follow that, but they can make changes. But they cannot make upside down.
Upside down.
You know, and this is how it's being done here. You know, in most of the cases. So they just give the design recommendation, not the actual design. You know, so the basic money contractor is going to make is through the value engineering.
Yes.
There is one thing called project management consultant. So there's another
The
option.
project management consultant do
Work
a
for the
very
client.
tough job, but is no one takes the liability. The major problem here is who is taking the liability. You know, the designer designed it. Whenever everything works unless until there is a failure, and when there is a failure, it's all about who blames whom.
Yeah. So in that case, who the designer is, if they are being the project management consultant, so they have the authority to check the construction. So there will be two teams. Like one team will be the designer and the project management consultant, and another team will be contractor. So there will
Is
be
there are very different methods. As long as there is being built right, it's fine. You know, but the coordination, the major coordination is really important. You know, because this system failure, this is not that's why I was talking about the system engineering approach. The system engineering approach works better if you do it design building. You know.
Yes.
But first you need to have the preliminary design done. Otherwise, you don't have any control.
Yes.
But there is also the other ways, like abusing the system because you don't follow a certain way of selecting the right team. You know, if you go through the design build system, they just given the money and given the power, they will come up with something, and then they will build, right? Yes. Anyway, thank you. So the last thing.
one of our team member is not present. I think building. Easy.
he's in Zoom, but you can give him a call.
I don't have his number.
How do I close this?
This one? Yeah, got it. It's not working now. Like
The pen drive got stuck.
The pen is stuck.
No,
No, the thing is, okay. No, which one? It's fine, if you, what you can do is. There's an issue.
Where is the
here.
pen drive?
Wait. This is the one, right? Yeah. Yes, both, yeah.
There's no one that comes?
Yeah.
Okay, so you finish your presentation, that's fine.
Okay, we will do this.
Okay, we can start with the rest of chair.
Okay, thank you. What is that?
Tilaji, are you there?
Can you see it in the Zoom?
Need to share this book.
Yeah. Hello everyone. We are group 2. One of our fellow classmates isn't with us right now, so don't worry. We'll just push through. Our topic was understanding the horrible dam failure and preventive measures for the future. I will not bore you with the what is dam and what not. I am just going to push through the about horrible dam. Well, it was located in California. Its construction began in 1961. It's an earthen embankment dam. Its height was about 770 feet, and width was about 6,920 feet. Its main purpose was water supply, flood control, and power generation. Okay. Next, the main structural features can be seen here. This is your lake Oroville. It has two spillways. One is the primary spillway, another one is emergency spillway. We can see that this is the main spillway, and this part is the emergency spillway, and this part is the dam.
Is a scholar.
Scroller.
Stand.
Oh, okay. Spotlight.
Yeah.
It's gonna go away. Okay.
We have to.
Okay. Oh shit. Sorry. Need something.
Try to use the pin right here.
But it's the same thing actually.
Oh,
Yeah.
Okay. Thank you.
thanks.
This is the Lake Oroville. And it has two spillways, as I said earlier. This is the main. It's supposed to be a point of Hmm? Sorry. Mouse. Can you see this?
Yes.
Okay, sorry. Sorry for the delays. This is Lake Oroville, and this is the emergency spillway. We are supposed to use it in the emergency conditions, and this is the main spillway. This structure is introduced in the dam to control the water reserved in the dam. This part is the main dam, and this is the hydropower electric center. So what happened in Oroville Dam was that it was built in 1968. So the design and other stuff was pretty backdated back then, but they proposed a proposal to upgrade this emergency spillway, saying that it was preliminarily an earthen spillway. So they proposed that this is not enough for this dam. There might eventually be failure. So the environmentalists suspected that, and they in 2005 they submitted a proposal for upgradation, but it was eventually rejected. In 2017 February 7, the weather forecast was there would be heavy rainfall in this period, and that eventually happened. And for that reason, the water capacity of that dam was raising to its maximum. So as usual, the operators were opened this main spillway, and they on February 7 they saw that there are some unusual water flow in this region. The water is not flowing as it is supposed to be, so they immediately shut off the gates of this spillway. And when the water cleared, they found that there are some erosions in there in the slab of this region. But as it was raining heavily upstream, so and their time was really of essence, so they couldn't prepare that on time. But the main problem was the water was rising eventually. The water was continuously rising. So the options they had was to should they open again this main spillway, or they use the emergency spillway, which never was used from the moment of the construction of the dam. But for deciding of this, for this, the time passed for the decision making, they eventually opened the emergency dam on February 11. But for their surprise, they saw that the emergency spillway is not working as it is supposed to be. The water is washing away the earthen material from the spillway. So, so the water is washing away the soil from the emergency spillway, which was not supposed to happen. So they then again they opened the main some of the doors of the main spillway in a controlled manner, so that the water shall not cross the highest capacity of the dam. Because if the water is above the highest capacity of the dam, there will be catastrophic failure, because main dam will be damaged. And also as the erosion is they saw the cutoff, the term they used in the report, that the cutoff was moving upstream. So if the cutoff reached this emergency spillway, then they would have no way to control this water. So the approach they took was to open this primary spillway in a controlled manner, so that the water doesn't rise above the emergency spillway. Also during this period, they found that they evacuated about 188,000 people from downstream to a safer area, and they keep doing this, that they are opening gate in a controlled manner, and so that emergency spillway is not used, and the main spillway gets eroded eventually, which can be seen in a simplified drawing here. So after passing this period, this is the aftermath of that time. This is the main spillway that we can see. The earth is washed away, and the main spillway has broken down. Also, we can see this is the emergency spillway, and there is earth eroding from here. So, as per the design, this was not supposed to happen, because this should just safely transport this water to the river downstairs, but that didn't happen. And so for this reason, the Association of State Dam Safety Officials and United States Society on Dams made a joint committee to investigate this incident, and they filed about 648 pages report, I think. But the main summary was that there are 3 flaws. One was design flaw, second was maintenance flaw, and third was role of weather condition. The design flaws were that they built the dam considering that the soil underneath was hard rock, but that was not the case. we can see from the previous picture that it was easily erodible material down there, but they didn't make the necessary changes while constructing the dam. Also, due to poor maintenance, the first damage that happened in the main spillway, that the slab washed away. It happened because the joint between the dams, the joint of the slabs between the main spillway were not thoroughly inspected and taken care of. As a result, there was a void formed, and when the water rushed down from upstream, water went down from that gap, and eventually there was an uplift pressure which flew the slab away. And once one slab was out, there was just a chain reaction, which eventually happened here. And also this also happened in the case of the emergency spillway also. The soil was not supposed to get washed away. It was supposed to stay in place, but the design consideration was it was a hard rock, but it was not. Also, also the weather condition was there that it was raining heavily upstream. So these are the main technical reasons, I think, for the failure of this dam. Next part of his presentation will be carried out by Fahim.
Thank you. So from the investigation, actually they found that it had different human and physical factors related to the failure, and it's a long-term systematic failure because there have been many warning signs, and later we can see that the owner was actually ignoring those signs, and there was some temperature variations that it was a progressive deterioration. It was not like abrupt or overnight failure, and it was under drains, and poor foundation was found at the spillway, and low anchor capacity and shallow underslab erosion. All was found from the investigation, but this was the first investigation in the USA, which actually considered the human factor for any failure investigation. And they found that the design service was not actually according to the system demand. So it was poor engineering, and the owner was overconfident about the infrastructure integrity, and the owner did not take any proactive approach, rather than they took the reactive approach. And they actually paid less attention to the spillway comparing to the main infrastructure.
That's the owner.
California Water Resources.
Water Resource.
California Department of Water Resources.
Yeah. In May that year, actually there was a public hearing, and they were criticized for their decision making and other things.
Not sued.
And I think there have been some issues with the state because they did not fund the repair, and the state had to pay a lot and everything. So
Okay, but then later on, there is no lawsuit.
I didn't find any case of the lawsuit.
There was a estimated cost of repair and recovery was 1.1 billion.
Yeah,
I'm not sure about
there's
the
supposed to be a lawsuit because of the poor maintenance. What happens? They need to evacuate,
Yeah.
right? So when they evacuate it, it's a forced evacuation, right?
Yes.
It's not a natural disaster, so it's a forced evacuation. So whenever there is evacuation, whoever is evacuated, some of them has like some emergency things, right? So someone may have lose their job, someone may have it has consequences. So someone needs to pay, right? If there is a consequence, there is definitely someone needs to pay. So who paid? That's why I'm asking.
I think the state, because I just found that the state had some issues with the water resource department because the state paid a lot.
Okay.
They just ignored the $100 million fund in 2005 for the repair of this dam.
So there's all the blame goes to them.
Yep.
They didn't pay that $100 million.
Yeah. So a lot of erosion debris were actually they clogged the Feather River below that dam. You can see the picture, and as Jurjan said, a lot of people are evacuated, and there are some fish and eggs and hatchery, which are also evacuated. And the power plant operations stopped, and of course, the repair cost of 1.1 billion. Kelechi, you can present, because he actually presented your slide. You want to present?
The implications and the consequences, so we have the implications and consequences, the immediate and long-term impacts, and also the human and the environmental impacts, which this talks about the displacement of residents, the ecological damage, and the loss of lives and properties, and the economic consequences. This talks about the infrastructure damages, the increased insurance costs, financial burden on affected regions. So the lesson learned and safety measures. So this emphasizes on the importance of robust designs, regular maintenance, and efficient risk management.
How to do the efficient risk management?
So how to do the risk management? We have to do the proper things like the reinforcing of the spillways, improving the concrete strength, and enhancing foundation stability.
Okay, so can you elaborate? Like if we are talking about the risk management, what are the components that needs to be added there? That is step one. What should be step one?
Dam strengthening.
Monitoring.
Monitoring.
Okay, the first thing is identifying the risk, the potential risk. So you need to do identification first, right? So for the identification, what you need to do?
For the identification, you have to so identify the problems. You have to
Do some background studies.
Do some background studies.
Okay, then
so after you do your background studies, you get to know about the problem and how to go about it.
how do you know the problem? Like if you do the background study, and if you want to identify the problem, what step we should take to identify the problem? Okay, let's move forward. No risk. We'll discuss that later. In the video? There was only this discriminatory. There was no breach. No breach, right?
They just got saved by breath of their hair. If the cutoff from the emergency spillway reached the emergency gate, it would have been breached.
They got lucky.
They were left.
And what is the problem with it?
We don't take this kind of risk.
Yeah, we shouldn't be lucky. We shouldn't be instructed to be lucky, right? If we need luck, then there is serious problem. Right?
And the interesting problem was that if they lose the dam, so the emergency spillway, they lose the powerhouse which operates the gates of the main spillway. So they had to be very careful opening the gates to such. They have to be very careful opening the gates of the main spillway to such way that it doesn't damage the downstream hydropower plant. Because if the power plant is out of the equation, then you cannot open or close the gates. It was a really interesting problem back then.
Okay, so their design was very poor.
Yeah.
Basically. But let's say they have a poor design. And what is the problem with it?
They didn't monitor it enough, and also they didn't updated the designs according to the new
Yeah, requirement, right?
According
So
to
let's say you identify a problem, you know there is a problem. And then you should also do something to fix the problem, right? So let's say they knew that there is a problem in the design, but if they knew there is a problem in the design and they disclose it, then they have to fix it, right? So what happens there is they don't want you to acknowledge the problem, right? If you're not acknowledging the problem,
and there is no problem.
then there is no problem, right? So, and that happens in many physical infrastructure. People know that it's not working, but it's there. So basically, the similar problem was existed for another industry. Exactly same problem existed for another industry.
When they first introduced the use of radium in watches, I read about that. They used radium in the watches that glow in the dark.
Yes.
But that had a potential health risk, but they didn't disclose it.
Okay, this sort of thing is there everywhere, but in terms of the infrastructure, it's like in terms of infrastructure, there was like a similar thing, which was the bridge foundation. You know, there are many bridge foundations. People didn't know in US that what is the foundation type, and if it has enough foundation or enough safety or not. Seriously. So what happened there is Congress passed a bill that every bridge has to be monitored every 2 years. So it becomes a line item. So whenever it becomes a line item and Congress passed a law, then that problem is being eliminated completely. You know, right now it's very rare that the bridge is failing in the US. It's very rare because every bridge, especially every bridge owned by the state duty, has to be evaluated. And it created a very big industry. You know, the next one comes with it. Do you know what is that? A similar regulation came into the picture.
The slope.
It's for the slope. They call it the landslide bill. So you have to monitor the landslides. You have to monitor, identify, monitor, and mitigate the risk of the landslide. It becomes a law. Now the regulation is coming, so it's like law is like one line. You know, it's like objective. The objective of this is to do this, but you have to explain it and you have to cover like with all the boundary conditions. So what you have to do and what you can and should not do with it. And there is no regulation for the dam. You know. So I think it's the time that the DQ or the state dam safety official, they're maintaining it and they're doing it. But I think it's not necessarily the similar way as the bridge monitoring program. So if the dam are being brought under the similar criteria, so many things will change. Okay, so in summary, what are the basic reason of the dam failure?
For maintenance.
For design and quality control.
Management. What is the if we want to do a design, then what are the factors that we need to consider or we should consider? Enough factor of safety. So technical things, right? And
Geologic conditions.
yes, silent restriction, very important. And yes, is being added, this is the new thing.
Climate change.
Construction.
Lifespan.
Okay, so whenever we are talking about the dam engineering, and if you're design it or monitor it or build it, it's a very big sector. It combines so many things. You need to have the proper engineering, proper design and construction, right? And then proper monitoring, because the system is there for a long time. So you need to monitor that, the maintenance, and then the operational practice. How it's being operated over the period of time, right? So the human factor, there are several failures because of the human factor, right? Cheated dam was also a human factor. Oracle dam is also a human factor. So you cannot ignore the human factor. And but if you look at the technical side of it, then what are the major criteria that we really need to follow and need to do the design?
We really need to investigate the site before designing any structure.
Okay, so let's say we have a good site investigation, but what are the factors we really need to consider to make sure that the design is right?
While construction, we should
not the construction, the design factors. What are the key engineering factors that we need to consider? If there is a potential for overtopping or not. If there is overtopping, it's always going to create a very challenging situation, right? Second, there should be no piping, right? So if there is a piping, it's quite impossible to reach the failure if there is a piping. The seepage should be controlled, right? Stability, the slope stability. Eventually there is a stability problem that will have, right? It failed. So it was the slope stability problem eventually because of the water intrusion, the soft interlocking with the foundation and the foundation soil and the hard strata, right? So it was a failure. So sliding problem.
Yeah.
And then there's the overtopping, sliding. There is also bearing facility problem, right? In the canal street, that was a sliding problem. So basically the overall stability of the things, right? Anything else? Erosion control, okay. If there is overtopping and you still need to be erosion control, okay. The erosion control is very important. Anything else? Compaction? Is the compaction is important?
Compaction.
Compaction is the issue. Why?
To reduce the permeability.
To reduce the permeability and
increase the bearing capacity.
increase the bearing capacity. Okay, very good. Yes, it's really important. Compaction is I think one of the most important factors in any art structure. And then let's say everything went right, but because of one thing is not right, it still may fail, or the lifespan may goes down significantly.
Extreme climate.
Very good. Material. The right material, using the right material. Now, Simon mentioned that if the right material is not there, it's always damaging. So basically, you need to know where the material is coming from, and then you have to update your design accurately. It's not like you just considering that all the material should come from one borrower, right? When this is a very big gap in every construction. Let me tell you this. Every construction guideline gonna tells you that you need to use this type of fill. You define a material properties, especially in earth structure. You define, let's say you have a certain soil with the certain liquid limit plus liquid index and the same, right? But how if the contractor is bringing that material and doing the construction right, how many testing has been done on that?
It's not possible to do enough.
It's not possible to do enough, right? So what is the best idea to do?
We usually take some sample from the material the contractor brings and test it randomly.
Randomly, right?
Yeah.
And let's say it fit in, and let's say it is not fitting in. Then what do you do?
If it's not fitting in the criteria set by the design, we request the contractor to make changes to the material he brings.
And then
this process goes on actually.
Okay, so let's say they keep changing the materials. So
Adjusting the design.
yes, instead of that, the better idea is go to the borrower and look at what material is there in the borrower. So contractor is never gonna bring the materials if it is more than 5 miles away, because the cost of the construction goes up significantly due to that, right? So the major thing is needed is to adjusting.
So we have to design with an open mind.
Designing with an open mind is not possible. It's like the key criteria you need to maintain the quality. So and that is tough. It's not easy because how that becomes a contractual issue. Basically, it's not an engineering issue. It's not a management issue. But how you are gonna execute the contract becomes a big issue, especially in big projects. Especially in big projects, it's very complex because they'll come up with something, one single clause that says that they can do it, and the other clause says they cannot. Now you have a arbitration and fight, and it's gonna kill the time. So whenever it's killing the time, you still need to pay. So your project cost goes up. It's a very common way of handling this type of issues, right? Anyway, okay, so as I say, the basic thing is this course is really fast. You have so many things to learn, and we need to cover so many things too. So from the next class, we're gonna start talking about the permeability and seepage. Okay, so we need there are like several manuals. The core of engineers manual I posted on the canvas is there. You can take a look. Especially the one we're gonna follow is the seepage manual. The seepage manual is really great. I think this is the Bible of seepage. Yeah. And
I think one of the manuals got updated 2022. I will send it to you. I think it's I'm not sure if it's the seepage or the flood wall designs. I mean the eye walls and the T walls and all those. I will check, but because I remember the last year they were talking about the new release. I'm not sure if they posted it yet, but I have a version of it. I can check and I'll send it to you.
Yeah. So you're also sending the report.
Yeah, I will send the IPIT report.
Yes. So I'm thinking maybe the follow-up of these discussions, I'm gonna make the term paper on that topic. So the term paper will be on like writing a review paper on the dam failures. causes and going with like several case studies, and then you have to write your own way of the basic problem and what are the things needs to be done, like that, you know.
We
Now-
choose the case study we want and write a paper about.
Yeah.
Okay.
And the other thing is, in this course, we need to discuss about the seepage first, seepage piping, the uplift capacity of all of it, and then before midterm is all about seepage. So after we finish the seepage, then there will be a project. Our project 1 will be on the seepage. And then the project 2 will be on the slope stability, but in between, I'm also going to cover the compaction and the drainage. So the design of the drainage structure and how we can do the right design for each own dam or embankment. You know. Okay, thank you. Any other question? No, thank you.
Thank you so much, Dr. Khan.
Thank you.
Have a good night.